I wait for it a little bit to join to YouTube. I would appreciate if you could share the link. Probably might be they cannot find. It's better to save this link somewhere so that we can always refer to it immediately. Okay. Now let us start today's lesson. You see, again, I'm starting with this title, second derivative, that we learned last time. But this time I want to talk again about local extreme points. So if you remember, I talked about a theorem called the first derivative test. Now we will talk about the second derivative test, not for inflection points and concavity of the graph of the function, but because it's another way to detect the local extreme points that we learned how to do it using the first derivative and setting up the sign table, the table with 3 rows, the first row x row, the second row f prime row, and the third row f row, yes? Now, after learning about second derivative, I am going back again to use the notion of second derivative, not for inflection points, but again for local extreme points. And again, I want to motivate you. So this is simple. So you see that I want to use the notion of second derivative, for example, to be able to detect this local extreme point. Or let me just make it a little bit bigger. So assume that this graph comes here and then goes back there. And then I want to detect this point as well. Of course, I was able to use the second derivative to find an inflection point, but this is not the topic of today's lesson. I want to use the notion of second derivative to detect, again, local extreme points, local maximum and local minimum. Okay, how can we do that? So let me make sure, am I muted or do you have echoes? Let me see. Yeah, no, that's correct. Okay, so now, how can I detect that? First of all, I know that the first derivative has to be equal to 0 if this is a well-behaved function, continuous function, differentiable. Continuous means that I can draw it with one pen stroke. Differentiable means that without any sharp points. Okay, the candidates are still the same. because the tangent line should be horizontal. Okay, so let me take this point to be point A and this point to be point B. If I ask you what is f prime of A, f prime of A, according to the notion of derivative, gives you the slope of the tangent line to the graph of the function at the point on the graph whose x-coordinate is A. That point is exactly this point, and you see that at that point, in a local extreme case, in a local maximum point, it should be horizontal, so the slope is 0. But now, if I ask you, what do you think about the second derivative at A? You cannot give me exact value, but you can tell me based on what we learned last time, if this is positive or negative. Yes, this we know. So you see that here, at this point, the concavity, this is concave, or I would say concave downwards. So you know that if this happens, last time we learned about that, the second derivative at that point should be negative. Okay? For the local minimum point, if I ask you what is f prime of what is f prime of A, what is f prime of B, you know that f prime of B is again 0 because still the tangent is horizontal. But now if I ask you what is f double prime of B, you cannot give me the exact value for f double prime of B, but you can see that it's convex at that point. It's like a normal ball, yes? It's concave upward. So then you would say that this second derivative is positive. So that is a very nice criterion, yes? So you see, when I wanted to find local extreme points in the previous, I don't know, 2 or 3 previous lessons, what we do, we take the derivative, we equate the derivative to 0, and we got the solutions to that equation. I told you these are just only candidates for the local extreme points. Okay, some of them might be fake one because it might happen that some of them are terrace points. Even if they are not terrace points, we didn't know which one corresponds to a minimum, which one corresponds to a maximum. For answering that question, do you remember we set up a table? We set up a table we called it the sign table. X, f prime, and f, and then you had A, the derivative is 0, f of A. Then you started checking the positiveness or negativeness of this f prime, and then you realize, for example, if this is positive, negative, it goes up, it goes down, it becomes a minimum, it becomes a maximum, or it might happen that this one is negative, this one is positive, then it goes down, it goes up, it becomes a minimum, or it might happen that both of them are positive or both of them are negative, then it becomes a terrace point. Now we found another criterion, sometimes much simpler to work with. Instead of setting up the table to realize which one of these points is a local minimum and which one is a maximum, we can do, instead of doing this, we can differentiate the function once more and check the number inside. If the second derivative at that point becomes a negative number, then it means that I am facing this situation. So it means that I am, this point corresponds to a max point, local max point. And if the second derivative at that point is positive, then what happens? It becomes a minimum point. But of course, there is also sometimes a drawback for this method. It is not as strong as this first derivative test, because I will tell you sometimes it cannot answer about, it cannot specify the nature of the point at hand. This is the topic of today's lesson that I want to talk about. So let me just write it here for you. The second derivative test. Of course, this is famous, but let me emphasize for local extreme points. This, what I showed you in this picture, I can write it here. So this is an algorithm again. So this is why I want you to have a good understanding of them, because the algorithms in this chapter are very close together. So there is a chance that you mix them up. But if you understand what's going on, even if you forget the content, because the content is not in the formula sheet, then you can actually think a little bit about that and then find your answer. Okay, so what we can do, we can say that number one, determine f prime of x. Number two, solve f prime of x equals to 0. Let x equal to a be an answer. Okay. Number three, determine f double prime of x. Number four, calculate f double prime at the point that you got in step 2. Number five, if f double prime of a is positive, so it means that the second derivative is positive, I am facing a local minimum point. If this, then a and f of a is a local minimum. Yes? If f double prime of a is negative, then I am facing the first situation. Then the point a and f of a is a local maximum. Yes? And unfortunately, if I am very unlucky, it might happen that the second derivative at that point also becomes 0. If f double prime is equal to 0, nothing related to the nature of the point a and f of a. So let me write no conclusion related to the nature of the point a and f of a can be drawn using this test. Instead of writing so much, I would say that the test is not inclusive. Everything can happen. If on top of that the first derivative is 0, the second derivative is also 0, it might happen that I am facing a local maximum point. It might happen that I am facing a local minimum point, and it might happen that I am facing a terrace point. So it is not inclusive at all. I cannot draw any conclusions. Then you might say that, okay, what can I do then? Unfortunately, it means that you have spent a little bit of time calculating these things for nothing, because If this happens, you have to go back to your original method, the first derivative test, to answer the question. Okay, so, but it doesn't mean that you don't need to know this. What I'm saying is that the first derivative test is capable of answering all of these. Okay, there is no exceptions. But when it comes to the second derivative test, especially for Math 3C lesson, this is a very good test because mostly the functions that you are facing are polynomial functions and exponential functions. And lucky enough, calculating derivatives of those functions are very simple. Yes? So this is good, not good, just it's very good to know, but you have to know because there are some questions that you need to know the concept. Okay, so let me give you some examples and follow this algorithm here. Then at the end, I will also talk about this situation, why this is problematic here when you want to use the second derivative test. So let me give you this example. Use the second derivative test. So let me write it like this, SDT, second derivative test. Use the second derivative test, if applicable, of course, to determine and classify the local extreme points of the following functions. Okay, so number one, f of x, let us start with very simple example. So x to the power of 2 plus 5x minus 1. Of course, this problem is actually very simple, but it's good to know about that. Okay, if I want to follow this, so if you don't mind, let me write A here so that I can write the numbers for the steps of the algorithm. So the first thing that I do, I take the derivative. Of course, this is a parabola. You already know that this should have a minimum because this x squared is positive. But just pretend that you don't know that to confirm it again with this method. You take the derivative, it becomes 2x plus 5. And then what you do, you equate it to 0. So number 2, f prime of x equals to 0. This gives me 2x plus 5 is equal to 0. It gives me that x is equal to minus 5 over 2. So far, this is a candidate for a minimum, a maximum, or a terrace point. Now, determine f double prime. Number 3, f double prime is very simple. You see, it's just 2. And then calculate f double prime at the point that you got in step 2 for all of them. So number 4, if I ask you what is f double prime of this number, it's very simple. Okay, what I am supposed to do, I am supposed to go to f double prime, remove the x, and replace it with minus 5 over 2. But this function is a constant. There is no x involved in the f double prime. So if I ask you what is f double prime of minus 5 over 2, hopefully you agree with me that the answer is 2. And now I go to the fifth step. If f double prime of a is positive, then it is a minimum. If it is negative, it's a maximum. So you see that the second derivative is positive. So what I see that this is positive. So I would say that the point minus 5 over 2 and f of minus 5 over 2 is a local minimum. And that actually is exactly what we expected of the parabola of this type. So you see, it is much simpler than setting up that sine table. So this is why I really recommend you to understand and use it effectively if necessary. Yes? Do you remember in the previous setup, after this step, I have to set up a table and determine the sign, positiveness or negativeness of the derivative, and based on that, conclude that this is a minimum. And of course, you shouldn't leave this in this form in the exam. You have to do the calculation. So, but let me just do it here in a scratch paper so then I can clean it. I put minus 5 over 2 here. It becomes 25 over 4. Minus 5 times that, it is minus 25 over 2. And then I have minus 1. So this becomes minus 25 over 4. So minus 29 over 4. Yes. Yes. So let me just clean that and write minus 29 over 4 instead. Okay. This is one simple example. Any questions? Is that understandable for everyone? Okay, so let us solve another problem. Because we don't need this, I want to keep the algorithm in front of our eyes for the time being. So let me just clean this example and then write part B here. Okay, so number 3, the part B. F of x is equal to one-third of x to the power of 3, and then minus 5 over 2 x squared plus 6x minus 1. I want to use the second derivative test, if applicable, to find the local extreme points of this function and classify them. Classify them means which one is maximum, which one is minimum. Okay, let me use the algorithm here. The first thing that I will do is to take the derivative. So this is the same actually as before. So this becomes x squared, this becomes minus 5x, and then it becomes 6. Number 2, you see it on the board. Solve f prime of x equals to 0. So this implies that I have x squared minus 5x plus 6 equals to 0. You can use ABC formula, PQ formula, or you know how to factorize this, hopefully. I use that one. That is up to you, which method you are more comfortable with. So I would prefer to write it as a product. I put one x here and one x here, and then I ask myself, I need two numbers whose sum is this number and whose product is this number. It's not easy, it's very easy to get actually. So minus 2 and minus 3, yes? So I put minus 2 in one of them, minus 3 in one of them. If I add them, it becomes minus 5. If I multiply them, it becomes 6. It's easier than ABC or PQ formula here. And then it means that either this one is 0, so x is equal to 2, or x is equal to 3. So these are my numbers. So far, everything is according to the previous method of the first derivative test. But now, at this stage, in the first derivative test, I will start setting up the sign table. But here, no. In this way, I will go to the second derivative. So I will calculate the second derivative, number 3. I take another derivative from this function. It becomes 2x minus 5. Okay? And then what I do, number 4, I calculate f double prime of a. But there are two numbers involved here. One of them is 2, one of them is 3. So I have to do this calculation for both of them. Yes. So this becomes f double prime of 2, f double prime of 3. So let us calculate them. If you want to calculate something about f double prime, so you need to refer to f double prime. I want to calculate f double prime at 2, so it means that I go to f double prime. Wherever I see x, I replace it with 2. So it becomes 2 times 2 minus 5. 4 minus 5 is minus 1. And it is important to see if it is positive or negative. So I was lucky. I would be unlucky if this turns out to be 0. If it is 0, I cannot decide about the nature of that point. Okay? Be careful. F double prime of 3, I put 3 here for the same reason. So it becomes 2 times 3 minus 5. So it becomes positive 1. This time, again, I am lucky, so it is not 0. The bad point is that if it turns out to be 0, then I would be in trouble for that particular point. Okay, so number 5, I need to draw the conclusion. Here, I can draw the conclusion for the nature of both of them. The one which gives me the negative 1, it corresponds to a maximum. The one that gives me the positive 1 corresponds to a minimum. So here, I would say x equal to 2, the point. So let me just write it simple. 2 and f of 2, let me write it, f of 2 let me write, I will write the answer in front, is a local minimum. Be careful. If it is positive, it corresponds to a minimum. Oh, sorry, it is negative. It's a local maximum. And then the point 3 and f of 3, I would write the answer in front later, okay, is a local minimum. Okay, and I think this is actually a boring calculation, so let me just do one of them at least. If I want to calculate f of 2, I have to go to my original function, replace x with 2 everywhere. So let me just write it with blue. So the first one becomes 8 over 3. The next one is 4. It becomes minus 10. Then this becomes 12. And then it becomes minus 1. So this becomes 8 over 3. This is minus 11 and plus 12. Yes? So it is plus 1. So it is 11 over 3. So then I would say 2. You have to do it in exam. 2 and 11 over 3 is a local maximum. And for this one, I have to plug 3 in. So let me just do that one as well. So if I put 3 in, then it becomes 27 divided by 3, 9. This becomes 9 minus 45 over 2. Then this becomes 18. And then it becomes minus 1. Yes? So here, 27 minus 1, 26. Minus 45 over 2, it's 7 over 2. Yes? So then it becomes 3 and 7 over 2. 3 and 7 over 2. So you see, it is very easy. Especially for these functions that you study in Math 3C. Because as I told you, most of the time you are facing polynomial functions and exponential functions. And they happen to be functions that are easy to differentiate them. Yes? Okay. Before moving to the next part, let me give you why this might happen. Why, if f double prime of a is equal to 0, I cannot draw any conclusions? Because everything can be possible in practice. So let me clean this and then start convincing you about that. If you have GeoGebra available, you can draw the graphs to confirm what I am saying. So let me consider 3 functions for you. I want to intentionally make them very simple. Okay? So the functions that I want to talk about is this function. F of x is equal to x to the power of 4. Another function that I want to talk about is g of x equals to minus x to the power of 4. And the next function, h of x, is x to the power of 3. Okay, so if you have GeoGebra available, so you can see that if you draw the graph of this function, it is very similar to the graph of the x squared, but a little bit sharper because it goes higher more rapidly, much faster than x to the power of 2. But these are essentially the same pictures. And this one is exactly this one. I am multiplying by negative sign, so it will be flipped over the x-axis. So it should be something like that for this function. And this function is also a famous function. If you draw the graph, you will see that this function at the origin has a trace point here. This is the function. These are the graphs of the function. Now, for all of them, I want to consider the origin. Okay? So now, if I ask you, what is this point for this graph? Or hopefully you agree with me, this is a local minimum point. If I ask you, what is this point for this graph? That's a local maximum point. And if I ask you, what is this point for this graph? You will confirm that this is a terrace point. Okay, now let us see what happens if I want to use the second derivative test to discover about the behavior of this point. If I want to do this for using second derivative test, what do? I take the derivative. It's 4x to the power of 3. I equate it to 0. And then 4x to the power of 3 is equal to 0. So this gives me x equal to 0. Then I take the second derivative. It becomes 12x squared. I am taking another derivative here. And then I put this number there. What happens? 12 times 0 is 0. So if I ask you, what is f prime of 0? F prime of 0 is 0. F double prime of 0 is 0. So you see f prime of 0 is 0. I am unlucky. F double prime of 0 is still 0. What is the nature of the point? The nature of the point is a minimum point. Okay? Let us do the calculation for minus x to the power of 4. It's extremely easy, yes? So let us just do it here. I calculate g prime of x. It becomes minus 4x to the power of 3. I put it equal to 0. Then it means that minus 4x to the power of 0 is equal to 0. So again, it gives me 0. I calculate the second derivative. It becomes minus 12x squared. I calculate the second derivative at that point. Again, unfortunately, it becomes 0. So if I ask you what is g prime of 0, you would say it is 0. What is g prime of 0? It is again 0. But what that point is, this point is maximum. Let us consider this function now. I calculate the derivative. It becomes 3x squared. I put it equal to 0. Then 3x squared is equal to 0, which means that x is equal to 0 again. And then I calculate h double prime of x. It becomes 6x. And I calculate h double prime at that point. Again, it becomes 0. So what happens? If I ask you what is h prime of 0, you would say 0. What is h double prime of 0? You would say 0, but it's a terrace point. So you see, when the first derivative and the second derivative are simultaneously equal to 0, the test is not inclusive. I cannot draw any conclusions because everything can happen. Yes, it can be a maximum, it can be a minimum, or it can be a terrace point. Okay, so be careful. This is a very simple, probably the simplest possible example that shows you that if you get the second derivative test, sorry, the second derivative 0 on top of that, the first derivative is 0, you cannot draw any conclusions about the nature of that point because it might be max, mean, or terrace, depending on the behavior of the function that you are investigating. So in that case, but this is not the weakness of the first derivative test. Let us check that. If I wanted to check the nature of this point, so here I cannot draw any conclusions because both of them are 0. The reason that I know it's a minimum because I already know the graph. And do you remember, the logic is the other way around. Okay, so here, if I want to check the nature of this point, what do I do? Let me just do it very quickly here. So I will take this sign table. I put 0 here. The derivative is 0. When I put 0 in the function, it's coincidentally 0 again. But then I need to check the sign here and there. I would say I choose a random number before 0, it's -1, and put it to my derivative. -1 to power 3 negative multiplied by 4 negative. And on the right-hand side, if I choose a random number, say 1, I put it here, it becomes 4, 4 is positive. And then you see that it goes down and it goes up, so I can immediately say that that is a minimum in agreement with the graph of the function. So, and then you can check these yourself. So what I'm saying is that the first derivative test is a stronger test. But you need to also know about the second derivative test. So this example, these 3 examples, is because I want you to understand the very last statement here. Okay, any questions? No. Now let me give you another example to see what happens. Let me again clean this part. I want to keep the algorithm. Okay, so let me write this. It's part C, I suppose, yes? F of x is equal to, let me give you an exponential function, for example, e to the power of, so I would write 2 e to power 2x, and then minus 4x plus 5, sorry for that. Okay, so this is my function. This is the same scenario. I want to use the second derivative test, if applicable, to determine about the nature of the extreme points. So the first thing, according to the algorithm, number 1, I take the derivative. So the derivative of this one is 4e to power 2x minus 4. Number 2, I put it equal to 0. Then what I get is that 4e to power 2x minus 4 is equal to 0. Then this means that e to power 2x is equal to 1. And then this means that 2x is ln of 1, or of course, it's much easier. So ln of 1 is also 0, so it means that x is equal to 0. So this is a candidate. But you see, taking the second derivative is very simple. Instead of setting up a sign table, I would myself prefer to use the second derivative test if I am lucky, yes? So f double prime, what is f double prime of x? 2 goes down, it becomes 8e to power 2x. And then what I need to do, I need to put this number in the second derivative. So f double prime of 0 is 8e to power 2 times 0. But 2 times 0 is 0, e to power 0 is 1, so it becomes 8. And I am lucky, 8 is positive. So this means that I can draw a conclusion, because the first derivative is 0, but the second derivative is positive. So this is this case. Yes. So what happens is that 0 and f of 0, which is what? 0 is 0. F of 0, it means that I need to go back to my function, put x equal to 0 everywhere. If I put x equal to 0, this is gone. If I put x equal to 0, it becomes 1 times 2 plus 5 is 7. Is a local minimum, because this is positive. Okay, any questions? Okay, now I will give you one more example, and this lesson is finished here. Let me give you another example. I will clean this. I designed something, and let me write it from what I have already calculated. So this is part D. F of x is equal to 3x to the power of 4 minus 16x to the power of 3. That's a good exercise to use GeoGebra to confirm these calculations graphically. Plus 24x squared and then minus 9. So let us solve this problem now. Okay, so what can I do? I want to follow this algorithm. So for example, if in the exam I ask you to determine and classify the local extreme points, full stop, then that's up to you if you want to choose the first derivative test or the second derivative test. But you need to be aware about the weakness of the second derivative test. That's up to you. But if I specify directly in the problem that, for example, use the first derivative test or the second derivative test to determine the local extreme points of the function and its nature, their nature, so you have to use exactly what I ask you in the exam question. Here, I have asked you to do it here, but you will see if I have done everything right. This is one of those examples that the second derivative test is not that helpful for all of them. This is something that you need to detect yourself to understand. So number one, I take the first derivative. It becomes 12x to the power of 3 minus 48x squared plus 48x. Okay. Number two, I put it equal to 0 and try to solve that. Of course, this is a third degree equation, but usually when I give these kind of questions, so it means that factoring this should be very easy. And in this case, indeed, it is very easy, because you immediately see that you can pull out a 12x. So this means that I have 12x, I take it out, it becomes x squared, this becomes minus 4x, and then this becomes positive 4 equals to 0. Of course, either this one is 0 or that one is 0, but I hope that you can also detect the pattern here. This is a complete square. If you don't detect, you can use PQ formula or BC formula. It will give you the correct answer. But at this stage, I think in the second grade, you should be very good in detecting this pattern. So this should be x minus 2 to the power of 2, the first one to the 2, 2 times the first one times the second one to the 2 is equal to 0. And you immediately realize that you have two roots. Either the first one is 0 or the second one is 0. So this means that either x is equal to 0, this is one possible point. The other one is that this is equal to 0. So this means that x is equal to 2. But these are just candidates. Okay, here we have decided to talk about the second derivative test, so I have to take another derivative. Okay, this is my first derivative. I take another derivative, it becomes 36x to the power of 2 minus 96x plus 48. Okay? Now, the step number 4, I have to put these values in the second derivative. F double prime of 0, I need to replace x with 0. Very simple. 0, 0, 48. And I am lucky because it is not 0, it's positive. So I can draw a conclusion immediately. I can say that the point 0 and f of 0, which is 0 and f of 0 is 0, 0, 0, 9, minus 9, is a local minimum. Okay? But if I have designed this correctly, hopefully these numbers are correct, let me calculate f double prime of 2. Then I have to replace 2 here. 36 times 2 to power 2 minus 96 times 2 and then plus 48. Hopefully this is correct. So 4 times 36 is 144. 144 and this one is 192. 2 times 96 is good. It's minus 192. So you see, unfortunately, this becomes 0. Okay? When it becomes 0, this is good. It was completely correct. But for this one, I cannot draw any conclusions using the second derivative test. Either you need to go back and clean everything from here to here, set up a sign table, but you can also just think about this point. You don't need to start everything from scratch again, because you were able to decide about the nature of at least one of them. One of them you couldn't detect anything about. You couldn't draw any conclusions. Now we don't need that. So let me clean this. If this happens, you need to know that you don't need to set up a complete sign table. You can make it minimal. Yes. So how? You, for example, you go here, you just set up a table. It doesn't need to be very complete. So you just put x and f prime here. And you don't need to arrange all of these numbers because you were already able to decide about this. So why should I include it here? I just put 2 here. The first derivative is 0 here. Okay? And now I just want to know about this particular point. Yeah? So what I do, I will go and choose a random number before 2. But this is a little bit, you need to be careful. For example, I am not allowed to choose minus 5 because I know that 2 numbers are important. For example, if you want to, you can write 0 here to make sure that when I say that choose a random number, you should choose your random number between 0 and 2, even if you don't write it down. Okay, so, but I don't care about the other parts. So let us choose the random number equal to 1, and I put it in the derivative. When I put 1 here, this term and that term are cancelled, so this is positive, definitely. So I would say it's positive here. And if I put a number bigger than 2, for example, 3, yes, if I put 3 there, it's positive again. How did I calculate it immediately in my head? Because if instead of putting it here, I realized that I factorized it here. So if I put a number bigger than 2, it doesn't matter. This is positive, and this is positive now. Yes, so it is positive again. So what is the nature of this point now? Even though I was not able to detect, I was not able to understand the nature of this point using the second derivative test, but it helped me actually, because I was able to say something about this point, so I make my sign table very minimal, and then I realized that this point is a terrace point, because before the point and after the point, the function is increasing. So yes, I would say that therefore, the point x, the point 2, and f of 2 is a terrace point. Okay, but of course, I'm a little bit lazy to calculate f of 2. If you want to calculate f of 2, 16 times that is 48. And then it's 8 times that is minus 128. And then you put 4 times this is 96. And then finally 9. Yes, so what's the answer? So this is 130 so far. So it is 2, 10, 16, 7. Yes, if I am right. You can check it. Don't trust me on that. So this point is 2 and 7, a terrace point. Okay, so you see that in this case, the second derivative is 0, and then we have to use the first derivative test to understand the nature of the problem, and it happens to be a terrace point. It could be very well be that this is a maximum point or a minimum point. No conclusion can be drawn at this point. So I wouldn't say that you have wasted your time so far, because you saw that for one of them, I was able to understand. For the other one, I make this table as minimal as possible, yes? Okay, any questions? Okay, good. So there are only two topics left from this chapter, and let us see how it goes. Then after sport law, we will talk about a good date for the exam, because I want to cover those, so I need 1 week to cover those topics, and then probably you need 1 week to practice. So then we can decide about the tests, so when it would be, so that it would be beneficial for everyone. And then, of course, the next chapter is about the integrals. The nature of those discussions are exactly the same, but then suddenly the last chapter is trigonometry and geometry, which is a completely, well, I would say, completely non-related subject, at least the way that we treat it in that chapter. Okay. So if you don't have any questions, thank you for listening. I will end this live stream, and then I will be available on Zoom if you have any questions. Thank you.